Control Systems, Chapter 6, Stability. In this lecture, we're going to learn how to determine stability, what it is, and how to determine it from the post-zero plot. First, why is stability determination important? Well, unstable systems are dangerous. Unstable systems can produce outputs that grow without bound, even in response to small inputs or disturbances. For example, you could have a drone that flips out of control mid-flight. You could have a cruise control system that causes the car to speed up indefinitely. Or you could have a robotic arm that shakes violently during a task and breaks something or hurts somebody. So in general, a system is stable if the natural response approaches zero as time approaches infinity. A system is defined as unstable if the natural response grows without bound as time goes to infinity. And a system is marginally stable if the natural response remains constant or oscillates as time approaches infinity. So the basic rule for stability is as follows. A system is stable if all poles of the closed loop transfer function are in the left half of the S-plane. In other words, the real part of each pole is negative. A system is unstable if any poles lies in the right half of the S-plane, which means the positive part of the S-plane. A system is marginally stable if poles lie on the j omega axis, the imaginary axis, but they must be simple. That's a multiplicity of 1. No poles can be repeated on the j omega axis, and all other poles must still be in the left half plane. So this is defined as a marginally stable system if it has these extra conditions. So why do poles matter? Well, poles matter to determine stability because poles correspond to the natural response of the system. Remember, the real part of the pole determines whether response decays, grows, or oscillates without decay. Zeros affect the shape of the response, but not the stability. So it's the poles that determine stability. So let's look at a few examples. So example 1. So say we solve and we find poles at -1, -2, -3. These are all in the left-hand plane, so this is a stable system. Example 2 is an example of an unstable system. If we have poles at -2, 0.5, and -1. So the 0.5 pole is in the right half plane, therefore our system is unstable. And finally, let's look at the case where we have a marginally stable system. We have poles at plus or minus j omega and -2. These imaginary poles have a multiplicity of 1. That's a marginally stable system. So in summary, to determine the stability from the pole zero plot, first thing we do is ignore the zeros since they don't affect stability. Second, locate all the poles. And third, apply the following rules. If all poles are in the left half plane, it's stable. If any poles in the right half plane, it's unstable. If you have poles on the imaginary axis, check the multiplicity for marginal stability.